Good afternoon. Good afternoon, and welcome to the Concrete Institute of Australia. I'm John Nichols, Technical Manager for the Institute. It's my pleasure to be your host for this afternoon's webinar, brought to you by NEXGen, Sustainable Solutions to Harvest Fly Ash and Repair Sewer Networks. This webinar invites two of our next generation to review two concrete sustainability projects from South Australia. The speakers are Weiwei Duan and Hossein Ataabadi. I'd now like to invite Eddie Guantong Huang to introduce our speakers. Ladies and gentlemen, please extend a very warm welcome to Eddie.
Thanks, John. Hello, everyone. I'm Eddie Huang, a member of South Australian Committee of NEXGen CII, and I'm pleasure to be introducing the speaker for this webinar. So first of all, let me introduce our first speaker, Weiwei Duan. Weiwei has been at the forefront of the field of sustainable construction material. Today, he will discuss his work on green cement applications, specifically focused on harvesting saltwater solute coal-fired ash in South Australia. His effort at Port Ancaster involved advanced methods to process fire ash that was previously captured using salt water solution refining technique to wash, dry, and enhance its particle size distributions. Please join me in welcoming Weiwei Duan.
Hey, thank you, John, and good afternoon, everyone. I'm Weiwei, a researcher specializing in green cement applications at the Harley Group. So first, thank you to the Concrete Institution of Australia for this opportunity, and also thank you to all for joining me today to discuss an exciting and innovative project that is harvesting saltwater sliced fly ash in South Australia. So at Harley Group, we are the South Australia largest integrated building, construction, and mining material supply company with a turnover exceeding $400 million. And our focus is on sustainability and innovation in construction materials. So our main office is at Dry Creek. So that is our main office. And today I'll walk you through how we are repurposing industrial byproducts like polyester fly ash to address pressing environmental and industrial challenges. To start with, let's have a brief look at the SEMs, the supplementary materials. So that materials, I think Hossein has already introduced about the SEMs, and that's used to partially replace the Portland cement to improve the durability, workability, and the mechanical performance as well. While at the moment, at the same time, it significantly reducing the carbon footprint of construction, especially the cement production. So as we all know, the cement production contributes to more than 12% of the total CO2 released every year. And depends on the chemical composition and the reaction mechanisms. The SEMs can be divided into two categories. The first one is we call it the polydentic SEMs. The typical one is low calcium fly ash. In Australia, we already have the standard to regulate this type of the SEM. And another type of SEMs, we call it latent hydraulic SEMs. Which the typical one is the most popular one is the GGBFS. And again, currently we also have the Australia standard to regulate this type of the SEMs. And the key things I think we here facing is that in Australia we're facing a critical SEM shortage. So that's especially in South Australia, we are 100%. So all of the SEMs, the typical SEMs, the fly ash and the slags are all currently imported. And what also makes the demand of the SEMs even higher is that our net CO2 net zero CO2 target by the year 2050. So to achieve that target, because firstly, our concrete demand is also increasing, and but we need to decreasing the CO2 releasing. So the result is that we have to use more SCMs to achieve that goal. In that situation, the estimation is that it will be 30% more SCMs will be needed by the year 2050. So, under that global and national pressure to reduce CO2, a new standard has been released, which is AS 3582.4, to allow use of the manufactured SEMs. So that's including the new SEMs, including mineral processing waste, incineration waste, and recover resources. So the new regulation and the new standards creates both a challenge and an opportunity for us. So we, Harley Group, has embraced the opportunity by identifying and developing new SCM sources in South Australia. So that is where we are looking, focusing on. So the South Australia's upper Spencer Gulf, that is the home to vast industrial byproduct stockpiles. So we currently have two focus. One is the Port Augusta flash dam with a stockpile of 20 million tons. And another one is the Near Star Port Pier polymatic smelter with 3 million tons of the fume slag. In addition to these two stockpiles, so this area also has the largest source of the renewable energy, which we may use in the future development. And to get use of these resources, we are planning to invest 130 million AU dollars in decarbonization activities that include securing long-term material rights that is already complete, and to launching a research and development program, which has already started for 2 years. And also, we will building infrastructure such as fly ash processing plant and state-of-art green cement distribution hub. That's this photo shows. It have the capacity of 52,000 ton cement storage, and have the two drives through the weight bridges, 100 tons per hour blend, and 15,000 tons SCM and flexible storage, and with another product silos and the third weight bridge. That's some other pictures of the dome I don't think it's almost finished at the Port Adelaide. Okay, then let's dive into this project, the Port Augusta fly ash. So that's the satellite map of the fly ash dam. So how to look like? So it's the area of the fly ash dam is about 260 hectare, and there used to be two power plant at their area, and they pump into the fly ash in this side, and so that the flow goes from the south side to the north side. And based on that, we start our R&D program that have two folders currently. The first stage is to understand the fly ash characters, especially the distribution along the spatial. We have to achieve this. We have investigated 130 sites across the dam, like it's like shows here. And for each site, we drill holes, and each holes have the 0.5 increments until it touched the natural ground. And we also review the slicing history and looking at the power plant information to get as much as the knowledge we know to harvest the fly ash here. And for the characters we are looking for, that include moisture at site, the moisture content, particle size, chloride content, TDS, and the loss on ignition. So these studies have provided us a detailed 3D profiles, we'll see it later, and helping us to identify the best place to offtake the flash. That is a photo of the flash taken from the different depths. So you can see that one is finer and that one's a little bit coarser. If you can see, I'm not sure you can see the particles here, but that one we can see definitely different from those two. It contains more moisture. Maybe it's close to the water table, or maybe it's the water flow have a high chance to flow in that area, so that causing a difference in the different depths. And that's also a photo of the flash we taken from the ground, and we can see that top one is the coarse particles, and there is the compacted layer with the finer maybe flash or something, and that is the medical particle size of the flash. And that is the photo of the flash we're taking back to the lab. So when we put all these samples in the truck, then we travel it back to the lab. That is what it look like. And that is the 3D profile we have investigated on the specs of the chloride, IOI, and that's the fineness, and this one is the moisture. So if we first look at the moisture, we found that the north side usually have the higher moisture. This is because we remember that the flash is pumping from this side, from the south side, then this side, then flow to that side. This causes a high moisture at the north side. So because the chloride is dissolved in the moisture, that causes so if we're looking at the chloride map, we find that in the north side, we have the relatively slightly higher chloride content than this side. And for the fineness is more related to the depths of the sample taking point. So this is because the fine things is easy to flow and the coarse things are likely to settle either. That is the particle size, overall particle size distribution of all the 130 size samples we have taken. So the D50, the average size is between 26 to 32 micrometers, is really fine. And there's the accumulation effect at around the 60 to 100 micrometers, and that needs us to further processing it to get it de-agglomerated. And so that's the first stage. We are trying to understand the flash characteristics, and followed by that, we have another stage, is to develop and optimize the flash processing methods. So the process method we currently include washing, dehydration, drying, de-agglomeration, and classification. To start with, we built a pilot plant at 1 to 10 scale at the dry creek to refine the technologies for chloride removal and also washing and milling of the coarse flash. And so that is the wash. That is the wash method we are using. That's the equipment we use to wash the flash. So that is like a disc filter. So the template here. So what they're gonna do? Sorry to stop it. So what that one gonna do is to, so we provided the vacuum at this pipe, and they will suck the water, and the flash will be blocked at the disc. Then we scratch the disc to get the dehydrated flash. And also we're looking at the water ratio and the different operation parameters, including the water rate, how many water we use to wash out the flash, and how long we should wash the flash. And we also try to get some relationship between the chloride content left in the washed flash versus all these parameters. So that's the result we are trying to get. And that's the photo of the de-agglomeration and the classification equipment in the pilot plant. Okay, and in addition to the currently we use the equipment, we're also looking at other chloride washing technique and also the dry techniques. So that's some results of the results of the washing, the chloride washing. So after 2 washes, we can get a 90% reduction of the chloride from the original box sample to around 0.05, which meets the ATIC limit. Okay, that is the result of the classification. So when we wash the fly ash, we try to separate the fly ash, try to separate the coarse and separate the fine one. And there will be 30% of the fly ash is very fine, lower than the particle size, lower than 32 micrometer, and the remaining is greater than 32 micrometer. So from here and after that, we're also looking at some chemical compositions and the mineralogy of the flash. So that is SEM photo we taken of the flash. So it's very typical ball-like particles without crystal pollutants. We cannot find that one in this SEM. And the chemical compositions, the large amount of the dominant amount of the silica and alumina, a little bit of the calcium, and that is the XRD results of the washed flash and the boxed flash. It's very typical crystal phases we can find. The first one is the quartz, which is very typical in flash, and the mullite, very typical in flash. And the difference is the highlight. So that one, we believe that's from the seawater. So after we wash the flash, that ones cannot detect it in the XRD results, which indicates that efficient washing process of the Port flash. Okay, so all this testing indicates that the processed flash could be suitable to use as SCM in concrete. To approve that, we put it into in making 40 megapascal concrete trials. So that is the result of the flash from different locations. And you can see that the strength is although the early strength is not as increased faster because that's a flash, that's a polymer material. All polymer material have the slower strength development at early stage, but after 28 days, we could see that the strength is similar or even higher to the reference samples, which only curtains the cement as they bonded. And that is we also investigate the different classification parameters so that we obtain the different particle size of the FA of the fly ash. We could see that this still have the comparable strength to the reference samples, and some of samples, the finer samples, the flash with the finer PSDs even have the slightly higher strength than the reference sample. Okay, so by harvesting the flash, we have already got some the environmental benefits, so such as the reduce the land use and minimize the CO2 releasing. But we believe we could still further maximize the environmental benefits. So what do we do to reach a target of the zero waste? So that is to use the washing water and the precipitation of heavy metals to ensure there's nothing left in the recycled water. That is the model. The schedule and the illustration of the pilot plant. Not the pilot plant. That's the real plant we would like to build at the Port Augusta. Okay, to sum up, this project gave us an idea on how innovation and the sustainability can transform industrial waste, the Port Augusta flash, into the valuable resources. But I believe there are some challenges, such as the management of the stockpile, the scaling up processes like washing and dehydration efficiency, and also the regulatory frameworks such as the chloride limits may need to adapt the new SEM resources. And finally, we invite you, industry partners, researchers, policymakers, to collaborate with us in this project. So together we can contribute to a more sustainable concrete and construction industry. Okay, thank you. Looking forward to your questions.
So just move to Hossein for our incoming presentation. Hossein Ataabadi is from UNSA, whose research focus on longevity and durability of cement tissue material. Hossein innovative research use waste treated sludge from drinking water treatment plant combined with calcium hydroxide. And this material was encapsulated with a 5 to 8 millimeter capsule designed to autonomously heal crack inside the sewer pipe and network system through positive reactions. So please welcome Hossein to share his research topic. Yep.
Yep. Thank you, Eddie. Hello, everyone. My name is Hossein Ataabadi. I'm the second-year PhD student at the UNSA. I'm currently working on a self-healing material using waste drive sludge. Yep, Yep, and I'm really honored to be invited as a speaker for this event. So just let's really glad to share kind of part of my studies with you. Okay, as you know that the concrete is one of the most consumed material in the world, specifically in Australia, because of its very decent properties it has. And it has a lot of application in different bridges, dams, road, and even it has been used many years for sewer system pipes, because mostly the concrete is very accessible and it has a decent compressive strength, and the cost of manufacturing is usually low, so it's a very decent material for using in construction applications. However, concrete has a kind of brittle nature, so it's prone this material to kind of cracking. So once the crack happens, usually it allows aggressive ions penetrate inside the concrete structure. And on the other hand, because the chemical resistance of concrete is low, so this penetrated aggressive substance or ions can cause corrosion, chemical expansion, and even shrinkage of the concrete materials. Another actually important problem, which mostly happen in sewer system pipes, is the microbiology induced corrosion, or MIC, which is mostly happen in this environment because of activation of microorganisms. In this environment, actually, the hydrogen sulfate from the sewer is transported to sulfuric acid, and it's reacted with the concrete structure and then cause the corrosion and change the concrete structure and material to a very soft material. In order to mitigate the MIC in this environment, a lot of research has been done through this last decades, but among all of them is actually one of the effective method is to improve the mixed design of structure and concrete that you are going to use in this environment. So different methods like addition of chemical surface coating, or even controlling the hydrogen sulfate gases level in this system has been done, but all this concluded to the improving the mixed design. So for improving the mixed designs, different sort of supplementary cementitious materials has been included to the mix design of the concrete. As you know, the SCMs or supplementary cementitious material has a lot of silica, aluminum, and calcium in the matrix, so it can react with the hydrogen products of concrete material or cementitious material and produce like extra gel, or we call it calcium aluminum silicate hydrates gels that can improve the mechanical and durability properties of the concrete, of the plain concrete as well. But through the last years, because of changing the supply and demands of the SCMs, amount of SCM that are available for use is getting lower and lower. So one of the approaches that all industry and academia are looking for is to find an alternative source of SCMs. In this regard, actually, drinking water treatment sludge is one of the materials that produced during the water treatment processes. Actually, based on increasing the water demand in both industry and domestic and pop and globalization, the amount of aluminum sludge has been increased. And because there is no very specific disposal method, so most of the sludge are disposed to the landfill. So this disposal actually caused a lot of costs. So just give you an example, annual production of sludge in a very mid-scale drinking water plant is 2,000 tons per year. So just imagine if we have 400 drinking water plants in Australia itself. So it's show you how much sludge is going to produce annually. And based on the estimations, its amount is increasing everywhere. A sludge, because it has a lot of aluminum inside its matrix, so it can cause some side effects, environmental effects. Actually, it's like CO2 emission. So it's increased the CO2, and leaching of aluminum to the water ground could cause some other source of disease such as Alzheimer. Okay, so one of the applicable methods of reducing the impact of sludge is use the sludge as a SCM in the cementitious material. So this is the work my group has been done through the last 5 years, and we had a lot of achievements. So once we incorporate the sludge to the cementitious material, because of its aluminum and silicon content, it actually changed the aluminum silica ratios inside the cement matrix, and it can improve the water penetration and improve the corrosion resistance of matrix, of cementitious matrix. So definitely it's improve the structure of the cementitious material. The whole thing is happen once the aluminum bearing phases that sludge has can react with the cement hydration. So increase some sort of calcium aluminum hydrates and produce some extra hydration products. So it can improve the corrosion resistance of the material. However, because the raw sludge has a lot of kind of organic material, is at the first, the raw sludge has around 29%. So before using the sludge in cementitious material, it needs some sort of pre-treatment. It could be crushing, calcining, or milling. So after pre-treatment, you can see that the amount of organic content reduced to 6%. And so the amount of aluminum and silicon increased very sharply. So it can be used in the cement material. Actually, sludge can be used as a sort of cement replacement, sand replacement, and even it could be used as precursor for alkali activated materials. So inclusion of sludge can have some economical solutions. So reduce the sludge that's disposed to the landfill, and it can improve the service life of the reduced products. In our new technology, actually, we are going to use sludge as a healing agent in concrete, which is actually part of my project. So, as you know, the self-healing concrete refer to sort of material that can heal themselves without any intervention. So concrete has a very intrinsic healing performance. We usually call it autogenesis. That's happened because of further hydration products of further hydration of unhydrated cement inside the matrix, and it can be improved by addition of some mineral admixture, fibers, nanofillers, or even curing agents. So this autogenesis progress mostly happen in pHs above 7.5. So we need a kind of alkaline environment for this healing performance to be happen. And the most important thing is it's very limited to the crack was less than 150 micrometer. So this shortcomings is like the concrete and the and autogenous self-healing is mostly depending on the concrete age, so it's need longer time, and it's need a kind of internal water resource that can that unhydrated cement particles can react and produce some gels. On the other hand, actually, there are different technologies that using supplementary materials and add them to the concrete structure to improve its self-healing performance. Different technologies are being used, such as vascular systems, using microorganisms like bacteria, and another method is using the capsule-based. Among all these technologies, actually, the capsule-based self-healing material shows the higher rate of efficiency compared to the other techniques. So in this regards, my project is going to encapsulate the sludge as a kind of capsule and include it into the cement material. So my project consists of 3 steps. The first step is just the production of the capsules and check its properties, morphology, and some related tests. After that, we will include the capsules into the cement mortar to see how it's affect the mechanical properties, and then after that we will have a look on the self-healing efficiency of the capsule into the mortar samples. For the production of capsules, as I mentioned before, we need a kind of pre-treatment. So the raw sludge actually goes under some grinding and calcination, and again kind of further grinding to find the final calcined sludge. So in this process, we not only reduce the particle size to around 8 micron, but also we will activate the sludge pozzolanic reactions by the calcination. Once we produce the sludge, we are going to mix it with calcium hydroxide and some other substance like actually in this process, the main core would be just sludge and calcium hydroxide. Also, we can add some other materials to improve the reactivity of these two materials, like superabsorbent polymers, like expansive materials. So we can include everything, all of this material together, and then we use kind of phase change material, which is called polyethylene glycol, call it PEG here. And once we melt the PEG, we mix it the core material with the PEG, and then do some mixing and produce the capsule cores. For the capsules, a thin layer of coverage that's prevent this core material react with the cement matrix. We need to provide a kind of shell or protective layer. So for the shell, we use another polymer, which is called ethyl cellulose. Is a kind of synthetic, is a kind of natural polymer under the cellulose categories. So we use cellulose, ethyl cellulose as a shell material. After some preparation, we have a shell solution, and afterwards we cover the cores with the shell material to produce our capsules here. In my project, actually, I produced one plain capsule. I call it C. It's like just the aluminum sludge and calcium hydroxide. And I had two other capsules as well. One incorporated of superabsorbent polymers, and another one is a kind of cellulose, expansive material like cellulose. So in total, I have 3 capsules that are going to add it to the cement material. Here you can see some morphology of the capsules. You can see the capsule produced is in a very spherical shapes, and you can see a very thin layer of the shell material all around the core material that cover the whole surface. And here is once we did some testing on the capsule. So after mixing, you can see some sand material attached to the capsule, and here is a one broken capsule. So even after breakage, the capsule retains its shapes and it's not degraded too much. Here is just 2 X-ray simulation. So we simulate the shell material and the core, so we could see if the core samples totally covered, and it's approved that the ore shell material that we selected can cover the whole core very good. We also did some SEM analysis. So if you see here in the right side, this area is the shell material, very smooth shell. So it's showing that the structure is really dense. So it can prevent water penetration inside the capsules during the mixing and preparation of cementitious material. Some forensic tests has been done to identify the structure of the capsules. All these tests actually confirm that the core material, because we use PEG, polyethylene glycol, as a kind of binder to bind all the powders we have together. So all these results showing that the PEG actually granulated all these core materials together. So if you see the peaks, all the peaks are in the final core material peaks. Okay, so after production of the capsule, it's going to use in the cement mortar samples. So we added the capsule in different ratios. So here I'm just presenting one of the ratios we have. Here we added 4% of the capsule by it's replaced by the sand to the mortar samples. So here we see that the compression and flexure strengths both reduce it around 20. The compression actually reduced around 30%, and the flexure reduced around 18 to 20%. So it's usually decreased. This decrease is because the capsule's interaction with the cementous material is not that strong, because the ethyl cellulose we are using is a kind of hydrophobic material. So the bond between cementous material and the capsule is not that strong. And also another impact could be the strength of the granules itself is less than the sand and coarse aggregates. So it's reduced the ore strength to some extent. So in terms of the self-healing efficiency, we had three to four type of tests. We test the mechanical strengths to see how it's recover the strength. So we crack the samples, like with this test, we generate some crack in the both cubic and beam samples, and then put them for healing time in different times to see how much strength will be recovered after the healing times. Another test we've done is to see what's the maximum actually crack that can be closed by the capsule. So we generate some samples and create some crack. It's a artificial crack with different widths up to 1 millimeter, and to see how much of this crack can be healed through the samples. Also, after the cubic samples production, we put a rebar on top to create a very single crack, and then measure and put some water on top of that and put the sample for the healing. So after different times, we measure that how much water penetrates through the sample. So it shows that how much the healing products that will be generated can prevent the water ingress inside the samples. So in terms of result, this is the compressive strength recovery. So we had three mixes with the capsules and one control sample. It's obviously show that the samples with the capsules recover the strength very more than the control samples. It's showing that it can generate healing products that can fill the cracks and denser the structure. Here is for the compression test, and this graph is for the flexure test. We had two different crack widths in the flexure samples. So one around 100 micron and 600 micron. So in both different crack widths, performance of the capsule incorporated sample was higher than the control one, showing that it has a very good efficiency. In terms of the water permeability or water ingress recovery, the maximum recovery we could achieve by the control sample was around 47% after 28 days, while we achieved this amount even in around 3 days with the samples that had the capsule installed. So it shows that our capsule are really fast responsive. So, and they react very fast, and they can heal the cracks very fast. Here, if you have a look at this bottom graphs here, it's the crack widths of different point. We select different points in the cracks and measure the void of cracks after various times, like the initial cracks after 1, 3, 7, and 28 days of healing time. So you just see in the control sample, maximum cracks we could heal was around 150 micrometer, while the sample contain the very plain capsules, just sludge and calcium hydroxide, can feel cracks around 400 micron, even 450 in some specific areas. So it's actually crack closure is around double than the control samples. And addition of 2 other supplementary material to the capsule core increase its closure rate. And in the samples, we had super absorbent polymers. It's the void it can be hit was around 800 micrometer. So it can actually heal a very large cracks. Here is some of the visual observation of cracks, and to see how the cracks actually filled. You can see some crystals generated in the crack surface or crack mouth because of further hydrations. And these 3 actually are the capsule with the supplementary material and the capsule itself. So you can see the cracks very filled with a very dense crystals here. And even the larger cracks can be healed with a combination of super absorbent polymer and the healing agent we have. Here is some other visual aspects like 3D observation of the cracks. And here is the X-ray simulation. So from here we could find the healing product from the capsules. Actually, the red one is the capsule and the blue is the cement matrix. The healing product from the capsules start to generate from inside the capsule and then goes outside and then fill this crack here. In terms of the microstructural analysis, mostly the most dominant products that's generated inside the crack was calcite, calcium carbonate, with in the control samples. But in the capsule incorporated, apart from the calcites, we had a lot of aluminum bearing phases like aluminum silicate hydrates, like the very thin particle within the calcite particles. Yeah, here are some forensics tested that's all confirm the presence of calcite, and the calcium silicate, calcium carbonates, it's all confirm the presence of this material. And in conclusion, actually, through the whole tests, we found that the cracks with around 1 millimeter, 800 micron, can be filled like within 7 days, showing a very fast responsive. And it's improved the recovery rates, strength recovery and water recovery more than the control one. And it's definitely will increase the service life of the structure we have. If you need more information, you can have a look at the recently published papers in these journals. And thank you very much for your attention. Thank you.
Good, thanks, Hossein, too. I'll just take remote control back.
Yeah, sure.
Yeah, sure. Yeah, thank you for the excellent presentation for both 2 speakers. So here we got few questions. So first questions for Weiwei. So regarding to the Harris fly ash, what's the performance of the Harris fly ash for the port and gas compared to like the conventional fly ash in terms of like compressed strength or durability?
Yeah. So that is a good question. So currently our testing show that the material have we do some test with the hot oxide flash as well as some flash from other sources, for the other typical flash directly from the power plant. We did the compressive strength and the mechanical performance showed that it have the very similar performance like as the typical flash. So that is for the second washed flash, we have the similar mechanical performance.
Yeah, so it's typically for the second wash fly ash, we got like equivalent performance to the conventional like the imported fly ash now.
That's right.
Yeah. Oh, good. So yeah, just another question from the audience. Like, does the fly ash met the AS 3582.1 standard? Because that's the standard like recently proposed for SCM.
Yeah, yes. That one's the casing is the chloride. We try to reduce the chloride things. So if the chloride is under that limit, that will be definitely satisfy that standard.
Yeah, sure. Of course, just one question for Hossein regarding to the capsule. So what's the cost for capsule? I understand like the capsules it's not that conventional technique for the current concrete industry. So what's the estimate cost for the capsule concrete?
Okay, so there's actually one main cost, because once we incorporate the capsule, the main difference between the capsule incorporated samples and the main concrete is just the capsule. So the difference is just for the production of the capsule. So for the main products of the capsules, sludge is already we have because it's donated to us, and we have a lot of it's a byproduct. We don't need to pay too much for that, but its pre-treatment needs some cost because we use the temperature for activation of the sludge, but its temperature is around 800 degrees, so it's definitely less than the cement production, which is around 100,000. And another cost is just for the peg, because it's kind of polymer, so we need to purchase that one, and the shell material, but both of them are very cost effective. So I think the cost increased around 20% or something. I'm doing the assessment right now. I haven't finished this part yet. But the service life advantage of this capsule is actually worth than like spending some money, and then it's reduced the maintenance cost for the future use.
Oh, sure. Thank you.
No worries.
So yeah, there's another questions from Liam Martin UTS for Weiwei. So just want like have you investigated the fresh property of concrete with the harvest fly ash in terms of like workability and rentations, and how they compare with the conventional materials like common OPC?
Yeah, that's the I think it's the conventional with the conventional flash. I guess that's the questions. So
Yep.
the flow, yeah, there's still this new flash, because you say the SEM images is still the round ball like particles. It have the very good ability to increase the workability and reduce the water demand when we're mixing with the concrete. And it have I believe they have the similar properties, work properties, to improve the workability, like the compared to the conventional flash.
Sure. So yeah, similar properties. So just another question for Roy as well for the fly ash. Like, are the particle of the fly ash affected like for the long-term storage? Particle size,
That
yeah.
yeah, the long term was whether the long term time storage could affect the flash property. We are still looking at that. Currently, I'm not quite sure of this answer. Because we're not sure so they have different depths. We're not sure which year is this depth and how the flash is flowing to that large dam. We are trying to figure out which year, so along the depths, which year is the flash mostly putting, which is the oldest flash we are trying to looking at. Then we can have investigation on whether where some reactions would occur to affect the particle size distribution of the flash.
Oh, sure. So just one like important question for fly ash. When will this fly ash be available for the market?
That's the question out of my scope. I cannot answer this question.
Yeah,
I
that
may
might be
check
the
it for
tricky
you
one.
with
Yeah.
my manager, yeah, and I answer this question later.
Yeah, that'd be quite tricky one. Yeah, just another question from Liam Martin from UTS as well for Hossein. So just for can the capsule be varied in size, and does this affect the workability of the mix? And is it comparable to the fly ash or another silicon another SCM materials like
Uh,
consider like in the capsule form like?
mhm. Yeah, actually the producer capsule I produce in projects currently is the size, the whole capsule is between 4 to 7 millimeter, is like a coarse aggregate for now. I've been included into the mixes in 2% replacement, 4 and 8. So increasing the percentage it definitely reduce it, the workability, and also it's reduced the strength because there's lots of pore structure on the capsule once we add it in the higher replacement rates. And in terms of compare with the fly ash and slag, I think the capsules, the polygalactic reactivity of sludge is is faster than the fly ash. So based on the things done, it's reacted within 7 days compared with fly ash and slag, which mostly have happened, I think 90 days or something. So it's a little bit faster. Yeah,
Oh,
a
sure.
little bit is quite faster.
Yeah, that's quite important for the fuelability as well. So another thing for the capsule self-healing tool, does the capsule or the post will test it on a long-term performance in the like a series pi like,
Yeah,
or it's
it's
just on
actually
experimental?
my next step. I'm preparing samples and definitely I will put them for the like durability tests, like a harsh environment. Even in some, we have some kind of sewage pipe there. We can put the samples in there, and even I will do some like acidic environment and alkaline environment tests in the upcoming test. So I'm just preparing samples, and then I will do
Oh, sweet.
this. I think in maybe I will do all these tests next year. Yeah.
Yeah, it's more practical. Yeah, just last one for Weiwei is like, what's an indication on the cost of the Harris fly ash like compared to the import one?
The indicate sorry, what the relative strength? The
Uh,
indicate
the cost of
the cost.
yeah,
So the cost for the
a Harris
for
fly ash production, I reckons.
that question I'm quite not sure at the moment, but I believe it should be the comparable to the
Yeah,
typical fly ash.
sure. Yeah, thank you. That might be all for the questions.
Okay, good.
Yeah.
And thanks, Eddie. And ladies and gentlemen, I ask you to join us in thanking our three speakers, Weiwei, Hossein, and Eddie.